Hey guys, so today's lesson is going to be on springs and Hooke's law. We are taking a hiatus away from rotational motion. It'll come back in a few weeks, and now we're going to analyze the motion of springs, and you will see that it's a lot similar to the motion. Our analysis of the motion will be a lot similar to how we analyzed particles in the before rotational motion. Anyway, so um, so far when doing our physics, yeah, we have made one assumption. We'll be making an assumption, and that assumption is that I'll go with blue. That assumption is that objects maintain their shape when forces act on it. This is an assumption that makes our analysis a lot less complicated, right? But this is not quite the truth, all right? Of course, there'll be questions that tell you to analyze the forces acting on a particle, and if they don't mention anything about analyzing its shape, they just keep assuming that the object will maintain its shape. But the truth is that forces cause solid objects to stretch, all right? They can cause a solid object to compress or even deform, all right? Even at the atomic scale, there's some deformation happening, all right? And we are going to study this kind of an analysis, of course, at a much larger scale, all right? And the best way to analyze the stretching and compressing of an object is by studying springs, all right? In this section, we'll study springs. So let's look at the behavior of a spring, all right? And before we actually get to that, let's get with some terminology, all right? We will refer to a spring at rest as being in equilibrium, all right? So if a spring has no forces acting on it, equilibrium in this context of springs means no forces are acting on it, all right? So that means that the spring is just alone, it's at rest, no forces are acting on it, all right? So we refer to a spring at rest as being in equilibrium. So anyway, so now when a spring is displaced from equilibrium, there is a force that tries to bring it back to equilibrium. This force is called a restorative force. All right, and we will see with some pictures clearly what this really looks like. I know it may seem abstract right now, but systems that experience restorative forces are called elastic systems. All right, and frankly, you would say everything is an elastic system, because truly, even at the atomic scale, we experience some kind of restorative force, all right? But if we want to measure how strong a restorative force is, we can talk about how elastic the system we're analyzing is. Anyway, so I just wanted these pictures here, these three pictures, just wanted to give you a small analysis, which we will build on. So when a spring is at rest, think of this as just like a wall, right? This is a wall. And the spring is connected with no forces on it, all right? When a spring is stretched, stretched to the foot, it will, this is what it will look like. It'll be stretched, all right, and it's stretched from equilibrium. And when it's compressed, it'll be this is what it looks like when it's compressed. All right, we're all familiar with strings, I believe. Anyway, so, and this section will be spent on studying the restorative force, and that restorative force is what we call a spring force. All right. In our picture, if I displace my string this way, right, my restorative force will be that way. All right, my spring force, I'm going to call it FSP. And if I compress my string to get back into equilibrium, my restorative force will be that way. So yeah, let's do more let's do more analysis, or let's figure out more concepts rather. So some key concepts now to know about the spring force is that the spring force, all right, I know this may seem a bit redundant, sorry. The spring force will always point in the opposite direction of, it will always point in the opposite direction of the displacement. All right. So if I'm pulling my string to the right, my spring force will be pointing to the left. If I push my string down, my spring force will be up, will point up. All right. Spring is a force, and the forces are vectors. So this direction I'm referring to is very, very important. And the second key concept I want you to get from this is that the larger the displacement, all right, the larger the displacement, the larger the spring force. All right. So what's this telling us? So here there is a proportionality relationship between the spring force and displacement. And our equation for spring forces in the vector version is FSP, that spring force, is going to be equal to K times delta X, or if you like, just X. All right, it's the same thing. So X here is the displacement from equilibrium. This FSP is the spring force. And then K is the spring constant. All right. So K is the spring constant. And why the negative sign? Well, this is because the spring force always points in the opposite direction of initial displacement. All right. So this is actually a vector. So let's say if we're talking about vectors, here we're referring to the x component of the spring force. So yeah. So here's a clearer picture for you just to visualize the displacement I'm referring to. It's an example from your book. So we talk about a relaxed spring, and that relaxed spring being displaced from equilibrium. So if we look at this picture, analyzing the compression, yeah, about equilibrium length here. So that at this point my spring is untouched. Nothing is acting on it. Then I put my hand to press it, right? To compress it. So the displacement, my delta X, will be from the starting position of my equilibrium length x naught to some length x1 where I where my hand at least fully displaces the spring. So that delta x we're referring to here is going to be x1 minus x naught, right? And we can see that if I displace this, I have a very good vector arrow here to show you that it's actually pointing in the opposite direction. And the same thing with stretching, Here again, we begin with a relaxed spring, no forces acting on it in its equilibrium length. And then we only count the displacement from the equilibrium length, that delta x, all right? So this is my x naught, right? And this is my x1. When we stretch, it's a bit, when we stretch, we can clearly see that x1 here is probably going to be negative and x naught will be positive. Let's say if this is our 0, it's going to be minus x naught. X naught is x1 is pointing to the left side, so on the left side is negative. So we'll see the signs get affected by these springs, as we'll see in questions we solve. So this direct proportionality relationship can be seen in a line. We can see that this is a function of x. The spring can be seen as a function of x, the spring force, and it just has a linear relationship with the slope as k. This is like saying y equals mx plus b, but b is 0, so we'll got y equals mx, and here y is just the force, and then x is our delta x, and m is k. Alright, it's a linear relationship, which we'll see in a lab this week. I got a lab for you guys this week. So anyway, let's talk about K, right? K is called the spring force. K is the spring force, has units in newtons per meter, all right? And what's its purpose? What does it do? It's a measure of how strong our spring is. All right, K is a measure of how strong our spring is. All right, so a larger K would mean the string is harder to stretch/compress. A smaller K, it would mean the string is easier to stretch/compress. All right, so that's really about K. Anyway, so let's try solve some problems, yeah? And let's try and solve a problem. So here is this is actually a fun problem. So several companies manufacture running shoes that have thick heel pads containing steel springs to launch a runner into the air after a heel strike. So when a 70 kg runner, so we have a 70 kg runner rocks back on his heels so that all of his weight is supported by heel springs. Okay, so there's springs in the shoes. The springs each compress by 1.2 millimeters. So that's our delta x. Our delta x is going to be 1.2 millimeters, which is also equal to 1.2 times 10 to the minus 3 meters. Because milli is a prefix. Milli, every time you see milli, this just means 10 to the power minus 3. So that's why I'm able to make that conversion. So yeah. Anyway, I'm going to write it in scientific notation because it's easier to do math that way. When he is running hard, he hits the ground on one heel, and the force compressing the spring is 5 times his weight. Interesting. So the force compressing the spring is 5 times his weight. So that's our spring force. Yeah? So now, what we want to find here is we want to find K. All right, find K. What is the spring constant? Yeah. Okay. This is a lot like what we've seen before. So if we say y, we begin by having a coordinate system, and we need a free body diagram. All right, and this free body diagram is the shoe, basically. All right, the shoe, or what's going on inside the shoe, and in the shoe there are springs, right? So let's say he's wearing 2 pairs of shoes. I'll assume that half the weight is on one leg and half the weight is in another leg, and then upwards we have the spring force. All right, and here you can see we're on in the y direction. So if we take the forces in the y direction, F of y is going to be equal to F spring force minus F 1/2 W. When a runner steps on the ground, at that particular moment in time, at that instant stepping at the time, we are in a static equilibrium. So F of y, if we apply Newton 2, because it's going to be equal to m-a-y, Newton 2 F of a-y will be equal to 0. So that's why this is here is going to be 0. FSP minus 1/2 weight. And then we can see, actually, sorry, this is not FSP, by the way. Apologies. Let's just keep it this way for now. We know that FSP here is going to be equal to 1/2 weight, and our FSP will be 1/2 mg. All right. So now the spring's restoring force. All right. The spring's restoring force. To find K comes from the Hooke's law. All right. So, and the spring restoring force here is 1/2 mg. So if I write my Hooke's law equation, FSP is going to be equal to Kx, yeah? And here I'm looking at the magnitudes, I'm not looking at the vector forms, so I'm not going to use the minus signs, delta x. And actually, because we're in a vertical direction, really, our equation will be K delta y, right? So thus, our spring force here will be 1/2 mg equals to K over delta y. All right? If I divide both sides by y. And at this point, it's just algebra. You can plug in for m. Okay, hold on. I want to write it clearly somewhere. So here you can see that K is equal to 1/2 mg over delta y. All right. So you can plug this into the calculator. You know what m is. You know what g is. M is 70 kg. G is 9.8, and delta y, we are told that the spring is compressed by 1.2 millimeters. So you can plug in 1.2. You gotta be in SI units, 10 to the minus 3 meters. Or if you like, this is I think 0.00012, something like that. Yeah. So 0.0. Apologies, it's actually 0. Let me write it nicely for you guys. 0.0012. All right. If you like, these two numbers are the same. So yeah, and that's how we solve K. We solve for K. And we want to know by how much do the springs compress in a heel strike. Okay, so for that, I think we might actually have to solve this. All right, I'm gonna shorten the video by only solving one question. Okay, so let me